Higher electricity practice test solutions. Question 1. Alternating voltage is displayed on an oscilloscope screen. The Y gain and time-based settings are shown. Which row in the table gives values for the peak voltage and frequency of the signal? Well, first of all, for the peak voltage, we want to look at the Y gain settings and the number of divisions to the peak. Our Y gain setting is set at 5 volts per division. First step in every calculation question, write down what you know. So 5 volts per division. We then look at the number of divisions we have. Here's our zero line. We have 1, 2, 3, 4 divisions up to the peak. So our peak voltage is equal to the number of divisions, which is 4, multiplied by the number of volts per division, which is 5, giving us 20 volts. For our frequency, we need to look at the time-based setting here. Our time-based setting is set to 1, but note the units here are in milliseconds. So we can say our time-based setting is 1 times 10 to the negative 3 seconds per division. We want to first find the period of the wave. We have a look at the wave and we can see that the wave is 1, 2, 3, 4 divisions in length, which means the period of our wave, capital T, is equal to the number of divisions, which is 4, multiplied by our time-based setting, 1 times 10 to the negative 3. That gives us a period of 4 times 10 to the negative 3 seconds. Period's not what we're trying to find out. We're trying to find out the frequency. Frequency, F, is equal to 1 over period. So our frequency is equal to 1 divided by 4 times 10 to the negative 3. This is why it's really important to make sure that you've looked at the units of the measurement, because if we hadn't taken into account milliseconds, we would have got the wrong answer. 1 divided by 4 times 10 to the negative 3 gives me 250 Hertz, which is row C in the multiple choice options in the paper. Question 2. The following circuit is set up. What is the reading on the voltmeter? Well, the reading on the voltmeter is the potential between the two resistors on the bottom of the circuit, which is also equal to the potential between the two resistors at the top. Now we're just going to use a potential divider equation here, but already I can see for the first section, this one here, my resistors have equal values. So that means my potential at the first part of the circuit, V1, is going to be equal to half of the supply, which is 6 volts. My potential across the 4 ohm resistor is what we want to try and find now. So what we need to do is use the potential divided equation. Remember, in the potential divided equation, we look at the proportion of the resistances and the proportion of the voltages. In this case, I'm looking at the 4 ohm. So V for the 4 ohm resistor is equal to R1 over R1 plus R2 multiplied by Vs. In this case, resistance 1 is 4. That's what we're looking for. R1 plus R2 is 4 plus 2 multiplied by supply of 12. That gives us 4 divided by 6 multiplied by 12. 48 divided by 6. Put this into your calculator, or you could work it out in your head. We end up with 8 volts. Now it's possible to look at this in terms of proportions as well. In this section, I've got 2 volts, 2 ohms rather, and 4 ohms here. So actually I can see that there's going to be twice as much voltage across my 4 ohm resistor as in my 2 ohm resistor, and the only combination of that adds up to 12 is 8 and 4. We haven't answered the question yet though. The question's asking what's the potential difference between the two sets of potential dividers. So I know that V1 is equal to 6 volts. I know that the voltage across the 4 ohm resistor is 8, so that means the potential difference must be 2 volts. On your sheet, that's answer B. Question 3. An electric motor in a golf cart is connected to a battery of EMF 48 volts and internal resistance of 0.52 ohms. We can see the circuit written there. We're told that the current in the circuit is equal to 22 amperes. First step in a calculation question, write down what you know. So the current is equal to 22 amperes. EMF is equal to 48 volts. Little r, the internal resistance, is equal to 0.52 ohms. And I want to find the lost volts. Lost volts is equal to current multiplied by our internal resistance. Now, in order to find the current, we're given it in the question. The internal resistance is given in the question also. So it's simply a case of multiplying those two things together, which gives you a value of 11 volts. As required, which is why this is only worth 2 marks. In the second part of the question, we're asked to calculate the output power supplied by the circuit when the current is 22 amperes. So again, I is equal to 22 amperes. We know that the lost volts from the previous part of the question is equal to 11 volts. We're asking to find power. Now, lost volts, remember, is the energy which we can't use. So that means the TPD, which is the energy we can use, is equal to the EMF minus the lost volts. EMF is 48. Take away our lost volts, gives us a value of the TPD to be 37 volts. Now you need to do this step first. This gives you 1 mark. We then use our power equation. P is equal to IV, which will give us a 2nd mark, and then substitute in the values. 22 multiplied by 37, giving us a value of 810 watts. If you didn't do this calculation first where you worked out TPD, you just went and used the equation P equals of IV and substituted in the wrong value of voltage, you would end up with just 1 mark. Obviously there are rounding errors here, so we would accept a range of values as long as your number of significant figures wasn't any more than 4. The driving force produced by the cart is now increased. State what happens to potential difference across the battery. Right, well, we've got to analyze the circuit here. If the driving force produced by the car has now increased, that means the power must have increased as well. P is equal to IV. If the current is increased, I goes up. That means that the lost volts, which we saw in the previous part of the question, which is equal to IR, also goes up. If the lost volts goes up, that means the TPD must have gone down, because lost volts plus TPD must always equal the EMF, which is constant within the question. Justification within an answer means that you're using an equation or relationship to justify your answer. Question 4. A 12-volt battery of negligible internal resistance is connected in the circuit as shown. The capacitor is initially uncharged, switch S is then closed, and the capacitor starts to charge. You're asked to sketch a graph of current against time from the instant switch S is closed. Numerical values are not required. But when a capacitor is charging, we start with a high initial current. That high initial current is determined only by the resistance in the circuit and the TPD, or rather the EMF of the source. The current then gradually decreases over time until it reaches zero. You should always put an origin within your graph. We're now asked to calculate the reading on the voltmeter at the instant when the capacitor ammeter is reading 5 milliamperes. Now, the resistance in the circuit determines the value of the current, but we also know that the current decreases over time as the capacitor charges. At this particular moment in time, we're told that current is equal to 5 milliamperes, which we should convert into amperes. That's 5 times 10 to the negative 3 amperes. So that means the current through the resistor is the same as the current in the circuit. So the voltage across the resistor is going to be equal to Ohm's law, current multiplied by resistance, which is 5 times 10 to the negative 3 multiplied by 500. Multiply that together, we get 2.5 volts. Now that bit there gives you the 3 marks. Question's worth 4 marks, which tells you you've got an additional bit of thinking. The voltmeter is connected across the capacitor. The voltage supply is equal to 12 volts. If I've got 2.5 volts of that across my resistor, that means the rest must be across the capacitor. So voltage across the capacitor is equal to the supply voltage, take away the voltage across the resistor, giving us a value of 9.5 volts. In part C, we're asked to calculate the maximum charge stored by the capacitor. Well, we know the size of the capacitance is equal to 47 micro, so that's times 10 to the negative 6 farads. We also know the supply voltage is equal to 12 volts. Therefore, the charge stored on the capacitor, Q, is equal to CV, so that's 47 times 10 to the negative 6 multiplied by 12 gives us 5.64 times 10 to the negative 4 coulombs. Standard 3 marks. The 500 ohm resistor is now replaced with a resistor of 2 kilo ohms. What effect, if any, does this have on the maximum energy stored by the capacitor? You must justify your answer. Well, let's look at the values. The equation for energy within a capacitor is E is equal to 1/2 QV, or 1/2 CV squared, or 1/2 Q squared over C. Now, none of these equations here have current in them. If I increase the value of the resistance, I'm going to decrease the current, which will change the time it takes for the capacitor to charge or to discharge, but it has no effect whatsoever on the maximum energy stored in the capacitor. So, no effect. Your justification is with the equations, but you should say values of C, that's the capacitance, and V, the supply, are unchanged. And therefore, Q is unchanged also. Question 5. This is our non-content question, and you'll have at least one of these within your exam paper. A student is investigating how the magnetic field strength at the center of a coil of wire depends on the direct current in the coil. The strength of the magnetic field is measured with a magnetic field sensor placed in the center of the coil. The sensor is connected to a computer as shown. The computer displays values of magnetic field strength. The unit of magnetic field strength is the Tesla. The student designs a circuit to vary and measure the current in the coil of wire. The circuit symbol for a coil of wire is shown. Draw a circuit diagram to show how the current in the coil could be varied and measured. Well, we should know in order to measure the current, we're going to use an ammeter. To vary the current, we need to use a variable resistor. Higher the resistance, the smaller the current. We also know that we're going to use the coil of wire. And of course, we're going to have some kind of supply. Now that supply could be a cell, or you could use a battery instead, or you could use a DC supply. But we have to make sure this is DC. An AC supply would not be accepted. So here are our components. Let's put them into the circuit. I'm going to select the battery. Connect that to my ammeter. Ammeter connected to my variable resistor. Variable resistor is going to be connected to the coil. And then connect the whole circuit together. Your 2 marks comes from selecting the correct components and making sure they're connected together properly. Question 5. The following results are obtained. You're asked to plot a graph of magnetic field strength against current. So here's the graph that we produce. Once you've plotted all the points, make sure your scale takes up at least 50% of your paper, then we need to draw a best fit line. A best fit line doesn't have to go through all of your points. It should be a straight line or a curve which best matches the trend. And we can see the trend here is vertically up, and actually the line that we can draw can go through 3 points. We can then use these points later on in order to determine a gradient. The student concludes that there is a systematic uncertainty in the measurements. Suggest the reason why the student has come to this conclusion. Well, we saw on the graph from the previous page that the straight line that we drew does not go through the origin. We would expect there to be a directly proportional relationship between current and magnetic field strength. This doesn't happen, and that would suggest that there is a systematic uncertainty causing the line to deviate away from the zero. So in answering this question, we say that the graph does not pass through zero or we could say that the magnetic field strength is not as we would expect. That is not zero when current is zero or the graph does not show a directly proportional relationship. Any would be accepted. 5D. The magnetic field strength V at the center of the coil of wire is given by the relationship V is equal to 6.3 times 10 to the negative 7 multiplied by Ni over R, where V is the magnetic field strength in Tesla, N is the number of turns in the coil, I is the current in the coil in amperes. R is the radius of the coil in meters. The number of turns in the coil used by the student is 30. Use this relationship and the gradient of your graph to calculate the radius of the coil. Now, we've got to think about how the gradient of graph is going to help here. So we have our relationship, B is equal to 6.3 times 10 to the negative 7 multiplied by Ni over R. Our graph is showing the relationship with magnetic field strength and current. So I can rearrange my equation. B is equal to 6.3 times 10 to the negative 7 multiplied by N multiplied by I, and then that's divided by R. I'm going to take the I from this side and bring it over to the other side. So I end up with B over I is equal to 6.3 times 10 to the negative 7 multiplied by N over R. B over I is the gradient of our graph. Now you can use any 2 points on the line on your graph in order to calculate the gradient. I work out the gradient to be 3.8 times 10 to the negative 4, and that would be Teslas per ampere. Your gradient might be a little bit out. We would accept anything between 3.8 times 10 to the negative 4 and 4.0 times 10 to the negative 4. And then take that value and substitute it in. So B over I is equal to 3.8 times 10 to the negative 4. And that's equal to 6.3 times 10 to the negative 3 multiplied by the number of coils, which we were told in the question is equal to 30, and divided by R. We can rearrange this again, bring everything to the other side. 3.8 times 10 to the negative 4 divided by 6.3 times 10 to the negative 3 is equal to 30 over R. So R is equal to 30 multiplied by 6.3 times 10 to the negative 3 divided by 3.8 times 10 to the negative 4, which gives us a value of 0.05 meters. Now the non-content question is simply a test of your arithmetic, your ability to rearrange formula, and your ability to select data from a question and put it into an equation. It doesn't need to be scary. Just follow the basic principles. First step in every calculation question, write down what you know. Question 6. The electrical conductivity of solids can be explained by band theory. The diagrams below or across show the distributions of the valence and conduction bands of materials classified as conductors, insulators, and semiconductors. Shaded areas represent bands occupied by electrons. The band gap is also indicated. Which material is a semiconductor? Well, a semiconductor has a small band gap, and that's because the conduction band and the valence band are close to each other. The valence band is full, the conduction band is empty, but because there's a small band gap, if we provide a small amount of energy, even thermal energy, to the semiconductor material, then electrons can be promoted from the valence band to the conduction band, at which point they can conduct. In an insulator, we have a very, very large band gap with a filled valence band, which means that electrons cannot pass this band gap and can't get to conduction band and don't conduct unless they break down. And in a conductor, the conduction band and the valence band are so close to each other they overlap, which means that we always have electrons within the conduction band. Semiconductor in this picture has to be material 2. A sample of pure semiconductor is heated. Use band theory to explain what happens to the resistance of the sample as it is heated. Now remember, as the material is heated, electrons can move from the valence band to the conduction band. By having electrons in the conduction band, some conduction can take place. Conduction is like the opposite of resistance. If I have lots of conduction, that means my resistance must be low. If I don't have a lot of conduction, the resistance must be high. So in this case, I can say that the resistance decreases. The reason why this decreases is because electrons jump from the valence band to the conduction band. Allowing conduction. Question 7 is our open-ended. Recent innovations in capacitor technology have led to the development of ultracapacitors. Ultracapacitors of a similar size to a standard AA rechargeable cell are now available with a rating of around about 100 farads with a maximum working voltage of 2.7 volts. By comparison, AA rechargeable batteries operate at 1.5 volts and can store up to 3,400 milliampere hours of charge. The charge in milliampere hours is equal to the current in milliamperes multiplied by the time in hours. Use your knowledge of physics to compare the advantages or disadvantages of using ultracapacitors and rechargeable cells. So I've just condensed this information down. Okay, so I've just taken the information and I've condensed it down a little bit to get the main points. Now, the most common reason why people don't receive full marks in the higher open-ended questions is because they don't answer it using higher level physics. So let's go straight in and have a look at the higher elements in order to get our marks. That means looking at capacitance. We know that the capacitance is equal to 100 farads. We know the operating voltage of the capacitor is equal to 2.7 volts. From that, we can calculate the charge using a higher equation, Q equals CV. And that works out to be 270 coulombs. Now remember from our National 5, Q is equal to IT. So a coulomb could be considered as an ampere second. We can't directly compare this to the charge that's on the AA batteries because it's in different units. It's in milliampere hours. So we're going to take our 270 coulombs and convert it to milliampere hours. 270 coulombs, 270 amperes at seconds is 270,000 milliampere seconds. Now if we divide that by 60 and then divide that by 60 again, we're going to get the amount of milliamperes in 1 hour. 270,000 milliamperes divided by 60 gives us a value of 75 milliampere hours. Now 75 milliampere hours is less than 3,400 milliampere hours. So I can say that the capacitor stores less charge. Now that's a good amount of physics, but probably only going to get you 2 marks out of 3. Another thing that we should look at is what we know about capacitors compared to batteries. And that would be that the capacitor charges very quickly. And that would be in comparison to a AA battery. We could also mention about the operating voltage for the AA battery being less than the operating voltage for the ultracapacitor. but we can add batteries in series and we could have a higher operating voltage. That's not really higher physics. It'll be more like National 5. So just writing that by itself is not going to give you any higher marks. We need to bring the higher physics in. This is probably the best way to do it. Obviously, open-ended question doesn't have one set of answers. We need to look at enough information in order to get the marks. Remember, to get 3 marks in an open-ended question, you need to show that you have a good conceptual understanding of the physics, providing a logical response. Good, not perfect. You must include, obviously, types of higher physics, relationships, equations. It doesn't mean the answer has to be excellent. It just means it has to be good. It doesn't even have to be complete. Now, if you've shown a reasonable understanding, you're only going to get 2 marks. If you've shown some but limited understanding, you're going to get 1 mark. But if you've shown none, no understanding at a higher level, there's wrong physics within your answer, a good deal of wrong physics, you're just going to end up with 0.